identify the terminals of charge controller and connecting battery to it, and the rest in part 2.
At the end of this video, you will be able to prepare wires for connection, wire the terminals of charge controller and batteries properly. Let us collect the tools, equipments and materials required to do this practical. Trainees Toolkit, solar panel 12 volt 100 watt, solar charge controller with user manual, connecting wires with lug, battery 12 volt 10 ampere hour capacity. Let us discuss the importance of charge controller in solar panel installation. A charge controller plays a crucial role in a solar panel installation by regulating the flow of electricity between the solar panels, the battery bank if present, and the load, devices or appliances being powered. In systems with battery storage, the charge controller prevents overcharging and deep discharging of batteries, which can degrade battery performance, reduce lifespan and pose safety risks. By monitoring the battery voltage and regulating the charging process, the charge controller ensures that batteries are charged optimally and kept within safe voltage levels. During periods of low or no sunlight, solar panels can act as loads instead of source of power, causing reverse current flow from the batteries to the solar panels. Charge controllers prevent this by blocking reverse current flow, protecting both the batteries and the solar panels from damage. Identifying the terminals in the charge controller. Pick the solar charge controller available in the lab. Identify the solar panel terminals, battery terminals and load terminals in the charge controller. Solar panel terminals. These terminals are where you connect the wires coming from your solar panels. They are often labeled as solar, PV or solar input. There are usually two terminals for connecting the positive and negative wires from the solar panels. Battery terminals. These terminals are where you connect the wires leading to your battery bank. They are usually labeled as battery or BAT and often have two terminals for connecting the positive and negative battery cables. Load terminals. Some charge controllers have terminals for connecting loads such as lights, appliances or other electrical devices. These terminals are typically labeled as load or load output. Connecting battery to the charge controller. Always connect the battery to the charge controller first. Connecting the battery first reduces the risk of electrical hazards during installation. Batteries store large amounts of energy and can deliver high currents, so connecting them first minimizes the chances of accidental short circuits or electrical shocks while wiring the rest of the system. Cut two lengths of battery cables, one for the positive terminal and one for the negative terminal of the battery. Strip the insulation from the ends of the cables to expose the bare wire. Slide the lug onto the stripped end of the battery cable. Ensure that the lugs barrel fits snugly over the exposed wire without any gaps or loose strands. Use a crimping tool, crimp the lug onto the stripper end of the battery cable. Once all the lugs are fixed to the battery cables, connect the cables to the appropriate terminals on the batteries. Tighten the terminal nuts or bolts securely to establish a reliable electrical connection. Polarities are more important in batteries because they determine the direction of electrical current flow within a circuit. Improper polarity connections can lead to short circuits, overheating, or even explosions in certain types of batteries. Maintaining correct polarity is essential for the safe and effective operation of electrical circuits and devices. Connect the positive terminal of the battery to the positive terminals of the battery terminal in the charge controller through a DC breaker or DC fuse in series. Connect the negative terminal of the battery to the negative terminals of the battery terminal in the charge controller and tighten the screws. Verify the polarity of the battery terminals and ensure that the positive and negative terminals are correctly identified and connected to the charge controller.
In this video, we have discussed how to identify the terminals in the charge controller, connecting battery to the charge controller. This concludes part 1. Thank you. Hello everyone. In continuation to the previous video where we learned to identify the terminals of charge controller and connecting battery to it, now we are going to learn how to
connect the series connected batteries to charge controller. Connect the parallel connected batteries to charge controller. Connecting the batteries in series to the charge controller. Take two batteries of 12 volts and 10 ampere hour capacity and place them in a suitable location. Identify the positive and negative terminals on each battery. Connect the positive terminal of the first battery to the negative terminal of the second battery using a wire. Now you will have negative terminal of first battery and positive terminal of the second battery. Identify the positive and negative terminals of the battery pack. The positive terminal of one battery should be connected to the negative terminal of the other battery. The remaining positive and negative terminals will be your measurement points. Turn on your multimeter and select the DC voltage measurement mode. Take the black negative probe of the multimeter and connect it to the negative terminal of the first battery. Then take the red positive probe of the multimeter and connect it to the positive terminal of the second battery. Ensure the multimeter display shows the sum of two battery voltages. When batteries are connected in series, the voltages of the individual batteries are added together. This means that the total voltage output of the series connection is the sum of the voltages of the batteries. Connect the negative terminals of any of the two batteries to the negative terminal of the charge controller. And connect the positive terminal of any of the two batteries to the positive terminal of the charge controller as shown. Connecting the batteries in parallel to the charge controller. Take two batteries of 12 volts and 10 ampere hour capacity and place them in a suitable location. Identify the positive and negative terminals on each battery. Connect the positive terminal of first battery to the positive terminal of the second battery. Connect the negative terminal of first battery to the negative terminal of the second battery. Turn on your multimeter and select the DC voltage measurement mode. Identify the positive and negative terminals of the battery pack. The positive terminals of the both batteries should be connected together and the negative terminals should be connected together. Take the black negative probe of the multimeter and connect it to the negative terminal of one of the batteries. Then, take the red positive probe of the multimeter and connect it to the positive terminal of the same battery. Ensure the multimeter displays the voltage of a single battery. When two batteries are connected in parallel, the output voltage remains the same as the voltage of a single battery. Connecting batteries in parallel does not increase the voltage, but it increases the total capacity and current capability of the battery bank. Connect the positive terminal of any of the two batteries to the positive terminal of the charge controller and connect the negative terminals of any of the two batteries to the negative terminal of the charge controller as shown.
In this video, we have discussed how to connect the series connected batteries to charge controller, connect the parallel connected batteries to charge controller. This concludes this exercise. Thank you. Hello everyone. In today's video, let us learn how to construct and test a 2 to 4 decoder. For ease of understanding, the video is split into two parts. Part 1 will contain the pin details of IC7408 and IC7404 and how to identify the pin numbers and fix the ICs on the breadboard, and then fulfill the next part of objective in part 2. At the end of this video, you will be able to construct and test a 2 to 4 decoder using AND, NOT gates and verify the truth table. Let us collect the tools, equipment and materials required to do this practical. Digital trainer kit, IC74LS04, IC74LS08, connecting wires, magnifying lens, Let us discuss the 2 to 4 decoders in simple terms. A 2 to 4 decoder is a digital circuit that takes 2 input signals and produces 4 output signals. The basic idea behind a decoder is to enable one of the multiple output lines based on the combination of input signals. Inputs and outputs. Inputs A and B. A 2 to 4 decoder has 2 input lines, usually labeled A and B. These input lines can be in one of the 4 possible combinations 00, 01, 10 or 11. Outputs Y0, Y1, Y2 and Y3. The decoder has 4 output lines typically labeled Y0, Y1, Y2 and Y3. Let's say A equal to 0 and B equal to 1, 0, 1. According to truth table, Y1 will be activated and the other output lines Y0, Y2 and Y3 will remain inactive. The decoder activates one of its output lines based on the binary input combination. For example, if A equal to 0 and B equal to 0, 0, 0, then Y0 is activated. If A equal to 0 and B equal to 1, 0, 1, then Y1 is activated. If A equal to 1 and B equal to 0, 1, 0, then Y2 is activated. If A equal to 1 and B equal to 1, 1, 1, then Y3 is activated. Let us discuss the pin details of IC74LS08 and IC74LS04. The IC74LS08 is a quad 2 inputs AND gate, which means it contains 4 independent AND gates, each having 2 inputs and 1 output. The AND gate output Y is high, 1, only when both inputs A and B are high, 1. Here, pins 1 and 2 are inputs and pin 3 belongs to output. This form an independent AND gate logic as shown in the pin diagram. In the same way, pins 4, 5, 6 form one independent AND gates. Pins 10, 9 and 8 form another independent AND gate logic, and pins 13, 12 and 11 form another independent AND gate logic. Pins 7 and 14 are for ground and power supply respectively. The IC74LS04 is a hex inverter, meaning it contains 6 independent NOT gates. Each gate takes one input and produces an inverted output. Pins 1, 3, 5, 9, 11 and 13 are inputs, and pins 2, 4, 6, 8, 10 and 12 are inverted outputs of the input pins. Pins 7 and 14 are for ground and power supply respectively. Construction and testing of 2 to 4 decoder circuit and verification of truth table. Collect all the components, check them, refer to the data sheet of the ICs and assemble the 2 to 4 decoder circuit on the breadboard. Identify the logic gates, ICs with their respective numbers. In this circuit, we are using 2 logic gates AND and NOT. These logic gate ICs can be identified by their part number printed on the top of the ICs. For AND gate, the part number is IC74LS08, and for NOT gate, the part number is IC74LS04. Using the magnifying lens, identify the AND and NOT gate ICs. Check that the ICs have 14 pins with no missing pins like broken or damaged ones. Identify the pin 1 on each IC. This is usually indicated by a small notch on one end of the IC or a dot near pin 1. Begin counting pins counterclockwise from pin 1. This means that the next pin is pin 2, followed by pin 3 and so on. After pin 7, count the pin 8 from the opposite to pin 7 in a counterclockwise direction. Place the IC on the breadboard. Position IC over the breadboard so that the pin 1 aligns with the notch or line on the breadboard. Carefully insert the IC into the breadboard, making sure each pin goes into a separate row of holes. Connect the input supply and ground to the ICs. Pay attention to specific pins that have special functions such as power supply, VCC and ground GND, inputs and outputs. Refer to the datasheet for your specific IC to understand the functions of each pin. From the pin details of IC74LS08 and IC74LS04, pin numbers 7 and 14 are allotted for ground, GND and supply VCC. Connect pin 14 and the power supply point plus 5 volts using the wires. And connect pin 7 and the ground point using the wires. In this video, we have discussed the pin details of IC7408 and IC7404 and how to identify the pin numbers and fix the ICs on the breadboard. See you in part 2. Hello everyone. In the last session, we discussed the pin details of IC7408 and IC7404, how to identify the pin numbers and how to fix the ICs on the breadboard. In continuation of the session, we are going to make connections on a 2 to 4 decoder using and NOT gates and verify with the given truth table. Refer to the user manual or documentation that came with the digital trainer kit. Look for a panel on the digital trainer kit that contains a set of toggle switches. Toggle switches are commonly used to represent binary values in digital systems. Each switch may correspond to a specific bit in a binary number. For example, in a 2-bit binary system, you may have 2 toggle switches, each representing 1 bit. Usually, digital trainer kits may have LED indicators connected to the output of toggle switches, indicating off for logic 0 and on for logic 1. In a digital trainer kit, output LEDs are commonly used to visually indicate the state or output of various digital circuits. These LEDs serve as visual indicators to help users understand the behavior of the circuits they are working with. Select any 2 toggle switches as input among the toggle switches from the digital trainer kit and name them S1 and S2. Connect the toggle switches S1 and S2 to the NOT gate IC74LS04 to pins 1 and 3 respectively as shown in the circuit diagram. Connect pin 2 of NOT gate to pin 1 of AND gate. Connect pin 4 of NOT gate to pin 9 of AND gate. Connect pin 1 of NOT gate to pin 13 of AND gate. Connect pin 3 of NOT gate to pin 12 of AND gate. Now interconnect pins 1 and 4 in the AND gate of IC74LS08. In the same way, interconnect pins 2 and 9, 5 and 12, 10 and 13 in the AND gate of IC74LS08 as shown in the circuit diagram. Identify any 4 LED outputs among the outputs in the digital trainer kit and name them as Y0, Y1, Y2 and Y3. Connect pin 3 to the output LED Y0, pin 6 to the output LED Y1, pin 8 to the output LED Y2 and pin 11 to the output LED Y3 respectively as per the circuit diagram. Verification of the output using the truth table. Use toggle switch S1 as input A and switch S2 as input B. Switch on the 5V DC supply and operate switches S1 and S2 for different logic levels, either in the 5-volt position or 0-volt ground position. Verify the readings on the table with the truth table of 2 to 4 decoder. Inputs A, B. Outputs Y0, Y1, Y2, Y3. Inputs 0, 0. Outputs 1, 0, 0, 0. Inputs 0, 1. Outputs 0, 1, 0, 0. Inputs 1, 0. Outputs 0, 0, 1, 0. Inputs 1, 1. Outputs 0, 0, 0, 1. Hope now you will be able to construct and test a 2 to 4 decoder using AND, NOT gates and verify the truth table. This concludes the session on construct and test a 2 to 4 decoder. Thank you. Hello everyone. In today's video, let us learn how to construct and test a 4 to 2 encoder. For ease of understanding, the video is split into 2 parts. Part 1 will contain the pin details of IC7432 and how to identify the pin numbers and fix the IC on the breadboard, and then fulfill the objective of this video. At the end of this video, you will be able to construct and test a 4 to 2 encoder using OR gate. Let us collect the tools, equipment and materials required to do this practical. Digital trainer kit IC74LS32. Connecting wires. Magnifying lens. Let us discuss 4 to 2 encoder in simple terms. A 4 to 2 encoder is a digital circuit that performs the opposite function of a decoder. A 4 to 2 encoder is a digital circuit that takes 4 input lines and produces 2 output lines. The purpose of an encoder is to compress multiple inputs into a smaller number of outputs. In a 4 to 2 encoder, the 4 input lines represent a 4-bit binary number, and the circuit activates a specific input line based on the binary input combination. It's commonly used in digital electronics for various applications such as data compression and signal encoding. Inputs and outputs. Inputs Y0, Y1, Y2, Y3. A 4 to 2 encoder has 4 input lines labeled Y0, Y1, Y2 and Y3. Outputs A1 and A0. The encoder has 2 output lines typically labeled A1 and A0. Let us discuss the pin details of IC74LS32. The IC74LS32 is a quad 2-input OR gate, meaning it contains 4 independent OR gates, and each gate has 2 inputs A and B and a single output Y. The IC operates with a standard positive 5-volt DC power supply voltage and requires a ground connection. Each OR gate within the IC74LS32 has 2 input pins A and B. These input pins accept binary input signals. Each OR gate also has 1 output pin labeled as Y. The output pin produces the result of the OR operation on the input signals A and B. The output pin will be at a logic high if at least one of the input pins A or B is at a logic high. If both inputs are at a logic low, the output will be at a logic low. Here, Pins 1 and 2 are input and pin 3 belongs to output. This forms an independent OR gate logic as shown in the pin diagram. In the same way, pins 4, 5, 6 form one independent OR gate. Pins 10, 9 and 8 form another independent OR gate logic, and pins 13, 12 and 11 form another independent OR gate logic. Pins 7 and 14 are for ground and power supply respectively. Construction of 4 to 2 encoder circuit and verification of truth table. Collect all the components, check them and assemble the 4 to 2 encoder circuit. Identify the logic gates IC with their respective numbers. In this circuit, we are using only OR gate. This logic gate IC can be identified by their part number printed on the top of the IC. For OR gate, the part number is IC74LS32. Using the magnifying lens, identify the OR gate with its part number IC74LS32. Check that the IC has 14 pins with no missing pins like broken or damaged ones. Identify the pin 1 on the IC74LS32. This is usually indicated by a small notch on one end of the IC or a dot near pin 1. Begin counting pins counterclockwise from pin 1. This means that the next pin is pin 2, followed by pin 3 and so on. Place the IC on the breadboard. Position the IC over the breadboard so that pin 1 aligns with the notch or line on the breadboard. Carefully insert the IC into the breadboard, making sure each pin goes into a separate row of holes. Connect the input supply and ground to the IC. Pay attention to the specific pins that have special functions such as power supply, VCC and GND, inputs and outputs. Refer to the datasheet for a specific IC to understand the functions of each pin. From the pin details of IC74LS32, pin numbers 7 and 14 are allotted for ground and supply VCC. Connect pin 14 and the power supply point plus 5 volts using the wires, and connect pin 7 and the ground point using the wires. In this video, we have discussed the pin details of IC7432 and how to identify the pin numbers and fix the IC on the breadboard. See you in part 2. Thank you. Hello everyone. In the last session, we discussed the pin details of IC7432, how to identify the pin numbers, and how to fix the IC on the breadboard. In continuation of this session, we are going to make connections on a 4 to 2 encoder using OR gates and verify with the given truth table. Refer to the user manual or documentation that came with the digital trainer kit. Look for a panel on the digital trainer kit that contains a set of toggle switches. Toggle switches are commonly used to represent binary values in digital systems. Each switch may correspond to a specific bit in a binary number. For example, in a 4-bit binary system, you may have 4 toggle switches, each representing 1 bit. Usually, digital trainer kits may have LED indicators connected to the output of toggle switches indicating off for logic 0 and on for logic 1. In a digital trainer kit, output LEDs are commonly used to visually indicate the state or output of various digital circuits. These LEDs serve as visual indicators to help users understand the behavior of the circuits they are working with. Select any 4 toggle switches as input among the toggle switches from the digital trainer kit and name them S1, S2, S3 and S4. In the 4 to 2 encoder using OR gates, note that the switch S1 is kept unconnected to the input as neither of the outputs depend on it. Connect the toggle switches S2 to pin 1, S3 to pin 4 and S4 to pin 5 in the OR gate IC74LS32 as shown in the circuit diagram. Now interconnect the pins 2 and 5 in the OR gate of IC74LS32 as shown in the circuit diagram. Identify any 2 LED outputs among the outputs in the digital trainer kit and name them as A1 and A0. Connect pin 6 to the output LED A1 and pin 3 to the output LED A0 respectively as per the circuit diagram. Verification of the output using the truth table. Use toggle switch S1 as input Y0, switch S2 as input Y1 and switch S3 as input Y2 and switch S4 as input Y3. Switch on the 5V DC supply and operate switches S2, S3 and S4 only for different logic levels, either in 5V position or 0V ground position as shown in tabulation. Observe the status of LEDs for each step of combinations and record your observations in tabulation. Verify the readings on the table with the truth table of 4 to 2 encoder given. Inputs: S1 Y0, S2 Y1, S3 Y2, S4 Y3. Outputs A1 A0. Inputs 1 0 0 0. Outputs 0 0. Inputs 0 1 0 0. Outputs 0 1. Inputs 0 0 1 0. Outputs 1 0. Inputs 0 0 0 1. Outputs 1 1. Hope now you will be able to construct and test a 4 to 2 encoder using OR gate and verify the truth table. This concludes the session on construct and test a 4 to 2 encoder. Thank you. Hello everyone. In today's video, let us learn how to demonstrate different flip-flops by the number printed on them. At the end of this video, you will be able to demonstrate different flip-flop by the number printed on the ICs. Let us collect the tools, equipment and materials required to do this practical. IC74LS73, IC74LS74, IC74LS76, IC74LS107, IC74LS109. Let us discuss on active low and high input pin details. An active low input can be identified from the pin details of the corresponding data sheets. A bar over the signal name or like a line over the signal often indicates an active low signal. Usually low level is 0 as represented here. An active high input can be identified from the pin details of the corresponding data sheets, whereas there is no bar over the signal name. Usually high level is 1 as represented here. Let us discuss about the IC74LS73. The 74LS73 is a dual JK flip-flop IC that belongs to the 74LS family, which is composed of two individual JK flip-flops, each with independent J and K inputs. It consists of two independent negative edge-triggered clock inputs, and this IC is designed for sequential logic applications and is widely used in digital electronic circuits. The 74LS73 IC typically comes in a 14-pin dual-in-line package, DIP. Here you could see the symbol representation of IC74LS73. Pin 1, clock input of flip-flop 1 JK1. Pin 2, clear input of flip-flop 1 JK1. Pin 3, input of flip-flop 1 K1. Pin 4, power supply plus 5V VCC. Pin 5, clock input of flip-flop 2 JK2. Pin 6, clear input of flip-flop 2 JK2. Pin 7, input of flip-flop 2 J2. Pin 8, complementary output of flip-flop 2 Q2. Pin 9, output of flip-flop 2 Q2. Pin 10, input of flip-flop 2 K2. Pin 11, connected to ground GND. Pin 12, output of flip-flop 1 Q1. Pin 13, complementary output of flip-flop 1 Q1. Pin 14, input of flip-flop 1 J1. Here you can see the logic connection diagram of the IC74LS73. Let us discuss about the IC74LS74. The 74LS74 is a dual D-type positive edge triggered flip-flops IC. The 74LS74 device contains two independent positive edge triggered D flip-flops with outputs. The 74LS74 IC typically comes in a 14-pin dual-in-line package. Here you could see the simple representation of IC74LS74. Pin 1, data clear input of flip-flop 1 D1. Pin 2, data input of flip-flop 1 D1. Pin 3, clock input of flip-flop 1 D1. Pin 4, preset input of flip-flop 1 D1. Pin 5, output of flip-flop 1 D1. Pin 6, complementary output of flip-flop 1 D1. Pin 7, connected to ground. Pin 8, complementary output of flip-flop 2 D2. Pin 9, output of flip-flop 2 D2. Pin 10, preset input of flip-flop 2 D2. Pin 11, clock input pin of flip-flop 2 D2. Pin 12, data input pin of flip-flop 2 D2. Pin 13, data clear input pin of flip-flop 2 D2. Pin 14, power supply plus 5V VCC. Here you can see the simple representation and logic diagram of the IC74LS74. The part number is usually printed on the top of the IC package. It may be a combination of letters and numbers, and it often includes the series name. Let us discuss about the IC74LS76. The 74LS76 is a dual inline JK flip-flop 16-pin IC, meaning it has two JK flip-flops inside with negative edge triggered clock input, and each JK flip-flop can be used individually based on our application. The JK flip-flops are the most efficient flip-flops and can be used for certain applications on their own. Pin details of IC74LS76. Pin 1, clock input of flip-flop 1 JK1. Pin 2, preset input of flip-flop 1 JK1. Pin 3, data clear input of flip-flop 1 JK1. Pin 4, input of flip-flop 1 J1. Pin 5, power supply plus 5V VCC. Pin 6, clock input of flip-flop 2 JK2. Pin 7, preset input of flip-flop 2 JK2. Pin 8, data clear input of flip-flop 2 JK2. Pin 9, input of flip-flop 2 J2. Pin 10, complementary output of flip-flop 2 Q2. Pin 11, output of flip-flop 2 Q2. Pin 12, input of flip-flop 2 K2. Pin 13, connected to ground. Pin 14, complementary output of flip-flop 1 Q1. Pin 15, output of flip-flop 1 Q1. Pin 16, input of flip-flop 1 K1. Here you can see the simple representation and logic diagram of the IC74LS76. The part number is usually printed on the top of the IC package. It may be a combination of letters and numbers, and it often includes the series name. Let us discuss about the IC74LS107. The 74LS107 is a JK flip-flop with individual JK direct clear and negative edge clock pulse inputs. The 74LS107 dual JK flip-flop has a total of 14 pins, which include input for two independent JK flip-flops, clock input for both flip-flops, outputs for both flip-flops, and complementary outputs for both flip-flops. Pin details of IC74LS107. Pin 1, input of flip-flop 1 J1. Pin 2, complementary output of flip-flop 1 Q1. Pin 3, output of the flip-flop 1 Q1. Pin 4, input of flip-flop 1 K1. Pin 5, output of the flip-flop 2 Q2. Pin 6, complementary output of flip-flop 2 Q2. Pin 7, connected to the ground. Pin 8, input of flip-flop 2 J2. Pin 9, clock pulse input of flip-flop 2 JK2. Pin 10, reset or clear input of flip-flop 2 JK2. Pin 11, input of flip-flop 2 K2. Pin 12, clock pulse input of flip-flop 1 JK1. Pin 13, reset or clear input of flip-flop 1 JK1. Pin 14, power supply plus 5V VCC. Here you can see the simple representation and logic diagram of IC74LS107. The part number is usually printed on the top of the IC package. It may be a combination of letters and numbers, and it often includes a series name. Let us discuss about the IC74LS109. The 74LS109 is a 16-pin IC consists of two independent JK positive edge-triggered flip-flops. The 74LS109 is characterized for operation from 0 degrees Celsius to 70 degrees Celsius. The feature of 74LS109 is a package. Pin 1, clear input of flip-flop 1 JK1. Pin 2, input of flip-flop 1 J1. Pin 3, input of flip-flop 1 K1. Pin 4, clock input of flip-flop 1 JK1. Pin 5, reset input of flip-flop 1 JK1. Pin 6, output of flip-flop 1 Q1. Pin 7, complementary output of flip-flop 1 Q1. Pin 8, connected to ground. Pin 9, complement output of flip-flop 2 Q2. Pin 10, output of flip-flop 2 Q2. Pin 11, reset input of flip-flop 2 JK2. Pin 12, clock input of flip-flop 2 JK2. Pin 13, input of flip-flop 2 K2. Pin 14, input of flip-flop 2 J2. Pin 15, clear input of flip-flop 2 JK2. Pin 16, power supply plus 5V VCC. Here you can see the simple representation and logic diagram of IC74LS109. The part number is usually printed on the top of the IC package. It may be a combination of letters and numbers, and it often includes the series name. Hope now you will be able to demonstrate different flip-flops by the number printed on the ICs. This concludes the session on how to demonstrate different flip-flops based on the number printed on the ICs. Thank you. Hello everyone. In today's video, let us learn how to construct and test 4-bit latch using IC7475. At the end of this video, you will be able to construct and test a 4-bit latch using IC74LS75. Let us collect the tools, equipment and materials required to do this practical. Digital trainer kit IC74LS75. Connecting wires, magnifying lens. Let us discuss about the IC74LS75. The 74LS75 is a quad bistable D-type latch integrated circuit, which means it can store and hold 4 bits of data. It contains 4 transparent D latches with a common enable gate on latches 0 and 1 and another common enable on latches 2 and 3. When Q follows D, latch enabled, the latch is said to be transparent. Construction and testing of 4-bit latch circuit using IC74LS75. Identify the 4-bit latch IC using a magnifying lens with their part number 74LS75 on top of the IC. Pin details of IC74LS75. Pin 1, complement Q1 output. Pin 2, D1 input. Pin 3, D2 input. Pin 4, enable 3 and 4. Pin 5, VCC, positive power supply. Pin 6, D3 input. Pin 7, D4 input. Pin 8, complement Q4 output. Pin 9, Q4 output. Pin 10, Q3 output. Pin 11, complement Q3 output. Pin 12, ground. Pin 13, enable 1 and 2. Pin 14, complement Q2 output. Pin 15, Q2 output. Pin 16, Q1 output. Collect all the components, check them by referring to the data sheet of the IC and assemble the 4-bit latch circuit. IC74LS75 has a 16 pins IC. Check that all the pins are straight and there are no missing, broken or damaged ones. Identify pin 1 on IC. This is usually indicated by a small notch on one end of the IC or a dot near pin 1. Begin counting pins counterclockwise from pin 1. This means that the next pin is pin 2, followed by pin 3 and so on. After pin 8, count pin 9 from the opposite side to pin 8 in a counterclockwise direction. Place the IC on the breadboard. Position the IC over the breadboard so that the pin 1 aligns with the notch or line on the breadboard. Carefully insert the IC into the breadboard, making sure each pin goes into a separate row of holes. Connect the input supply and ground to the ICs. Pay attention to specific pins that have special functions such as power supply, VCC and ground, inputs and outputs. Refer to the datasheet for a specific IC to understand the functions of each pin. From the pin details of IC74LS75, pin numbers 12 and 5 are allotted for ground and supply VCC. Connect pin 12 to the ground point and connect pin 5 to the power supply point 5 volts using the wires. Select any 5 toggle switches as input among the toggle switches from the digital trainer kit and name them S1, S2, S3, S4 and S5. Connect the toggle switch S1 to pin 7. Connect switch S2 to pin 6. Connect switch S3 to pin 3. And connect switch S4 to pin 2. as shown in the circuit diagram. Make a short between the pins between 4 and 13 using jumper wire and connect either the 4 or 13 pins to switch S5 as per the circuit diagram. Use toggle switch S1 as data input A, switch S2 as data input B, switch S3 as data input C, switch S4 as data input D, and switch S5 as enable or clock input. Identify any 4 LEDs as outputs among the outputs in the digital trainer kit and name them as QA, QB, QC, QD. Connect pin 9 to QA, 10 to QB, 15 to QC, 16 to QD. As shown in the circuit diagram. Switch on the 5V DC supply and operate switches S1 to S5 for different logic levels either on 5V position or 0V position as shown in tabulation. Set the toggle switch S5 enable or clock to the off position or 0. Set the input toggle switches at different logic levels and record the output in the tabulation. Similarly, record the output for the S5 in on position or 1. Inputs S1, S2, S3, S4, clock S5, outputs QA, QB, QC, QD. Inputs 0, 0, 0, 1, clock 0, outputs 0, 0, 0, 0, clock 1, outputs 0, 0, 0, 1. Inputs 0, 0, 1, 0, clock 0, outputs 0, 0, 0, 1, clock 1, outputs 0, 0, 1, 0. Inputs 0, 0, 1, 1, clock 0, outputs 0, 0, 1, 0, clock 1, outputs 0, 0, 1, 1. Inputs 0, 1, 0, 0, clock 0, outputs 0, 0, 1, 1, clock 1, outputs 0, 1, 0, 0. Inputs 0, 1, 0, 1, clock 0, outputs 0, 1, 0, 0, clock 1, outputs 0, 1, 0, 1. Inputs 0, 1, 1, 0, clock 0, outputs 0, 1, 0, 1, clock 1, outputs 0, 1, 1, 0. Inputs 0, 1, 1, 1, clock 0, outputs 0, 1, 1, 0, clock 1, outputs 0, 1, 1, 1, and so on. The rest of the values can be seen in the table. Hope now you will be able to construct and test a 4-bit latch using IC74LS75. This concludes the session on how to construct and test a 4-bit latch using IC 7475. Thank you.
Jai Hind. Today I am here to discuss about the importance of tender presentation. Tender presentation is a critical state of tender formulation and tender procedures. It is usually done after the issue of tender documents and